The electrical system plays a key role in engine operation and performance. In this video program, you'll be introduced to electricity and its behavior in the electrical systems of Kohler engines. A brief overview of electrical theory will help you understand the components of an electrical system and how they interact. Electrical terminology and testing methods will be explained in easy-to-understand language to help you comprehend the concepts and become more proficient in working through real situations. Finally, we'll demonstrate the use of common meters to expose you to the basics of troubleshooting scenarios you may encounter in daily service work. All matter is made up of atoms. Similar to our solar system, with the sun in the center and planets in orbit, each atom has a center portion, called the nucleus, with one or more electrons in orbit. The electrons have a negative charge and are held in their atomic orbit by the attraction of a positive charge in the nucleus. In some materials, the attraction is quite weak, and the electrons can move from one atom to another quite easily. Electricity is the movement of electrons from atom to atom through a material. Materials that allow electrons to move easily, or flow, are called conductors. Conductors are used to carry electricity. Other materials hold their electrons tightly, so they do not move easily from one atom to another. These materials are called insulators. Insulators are used to isolate and contain electricity in the desired conductors. Electrons can be made to move in materials by several methods. One very common method is by rubbing materials together to transfer electrons from one article to another. This is called static electricity, and it causes the zap that we feel when our bodies have been charged with electrons rubbed off items like clothing or carpet, and then suddenly discharge. Static electricity is not used in engine electrical systems. Electron movement can also result from chemical reactions. The best example of this is a lead-acid storage battery, which is common in engine applications. Lead-acid batteries have a series of positive electrode plates connected to one battery terminal, and negative electrode plates connected to the other terminal. The plates are suspended in sulfuric acid, and the chemical reaction with the acid results in a flow of electrons from the positive plates to the negative plates. The negatively charged electrons collect on the negative plates, giving that terminal a cumulative negative charge or potential, thus the name negative terminal. As the electrons migrate away, the other terminal develops a positive charge or potential and derives its name, positive terminal. If a path of conductor material is established between the terminals, the excess electrons at the negative terminal will force a flow of electrons through the conductor to the positive terminal. Such a conductor path is called a circuit, and the flow of electrons through the circuit is referred to as current. If we add switches and electrical load devices to our circuit, such as lights or coils, we can control the flow of electricity and make it do work as it proceeds through the circuit. Some of the electricity is transformed to other forms of energy within the circuit and loads, so the battery will begin to discharge. As it does, the chemical reaction inside changes the sulfuric acid to water, and the electron output from the negative terminal gradually decreases until the battery is fully discharged. Sending a reverse flow of electrons through the battery reverses the chemical reaction, bringing the battery back to its full potential. This is what occurs when a battery is charged by a battery charger, alternator, or generator. The force field of a magnet can also cause electrons to move. A magnet is surrounded by a force field called flux. The North Pole has a positive charge and will attract electrons. The South Pole is negative and will repel electrons. If a conductor enters a magnetic flux field, the magnetic force overcomes the attractive force of the atomic nuclei. The electrons leave their orbit and begin moving through the conductor. This phenomenon is known as electromagnetic induction. If the conductor in the flux field is part of a circuit, the electrons will flow through the circuit as electric current. The force or pressure of the electrons trying to push through the conductor is referred to as voltage, measured in volts. The rate or volume of current flow is known as the amperage, measured in amperes, or just amps for short. Anything that opposes or reduces the current flow is referred to as resistance, which is measured in ohms. These three factors, voltage, amperage, and resistance, are present in any circuit with current flow, and they have a definite and exact relationship to each other. The easiest way to understand the relationship is a comparison to water flowing through a pipe. If you get a buildup of rust or scale in the pipe, it reduces the flow and causes a drop in pressure. Similarly, increased resistance in a circuit reduces the amperage and causes a drop in voltage downstream from the resistance. The relationship was originally expressed in Ohm's law, but it can be best illustrated with the mathematical formula volts equals amperes times resistance, or E equals I times R. If any two of the values are known, the third can always be calculated. A circuit with low resistance that allows current to flow easily is said to be continuous or closed. Another way it is often stated is that a closed or complete circuit has continuity. A circuit with very high or infinite resistance, such that no current flows, is an open circuit. It will not have continuity. Some elements in a circuit may have undesirable resistance, which is reducing current flow and circuit performance. Examples are undersized wire, poor connections, corroded terminals, and burned or glazed switch contacts. Components in a circuit which do work have resistance. Examples are light bulbs, electromagnets, coils, and heating elements. The resistance imposed by a working component is referred to as a load. Other components such as switches and resistors use resistance to control the circuit. These are examples of conditions where resistance is desirable and put to use. There are two basic arrangements of components in a circuit. When a circuit is arranged with loads one after the other with a single current path, the circuit is called a series circuit. The voltage drop through each load is in proportion to its resistance. Higher resistance results in greater voltage drop, since more pressure is required to push current through higher resistance. The total voltage drop from all combined loads is equal to system voltage. When a circuit is arranged with loads parallel, or next to one another, with multiple current paths, the circuit is called a parallel circuit. Because each load in a parallel circuit is connected between positive and negative, the total voltage drop from each load is equal to system voltage. A circuit fault, which results when a current path finds continuity and takes a shortcut without completing the normal circuit, is called a short circuit. In troubleshooting, a short will always be parallel to the intended circuit path. Now that we have introduced and defined each of the terms used in understanding electricity, we'll use some basic test equipment to confirm circuit behavior and performance. A voltmeter is used to measure the voltage between 2 points in the circuit and is connected in parallel to portions of an active circuit. The black negative connector is attached to the end of the circuit connected to the negative battery terminal. This is usually referred to as ground. The red positive connector or probe is touched to the conductor at points where the conductor is exposed, such as connectors and terminals. Because the meter is attached parallel to the circuit, readings at any point between the positive battery terminal and the load should register full circuit voltage. However, if a high resistance exists in the circuit between the voltage source and test point, a reduced voltage will be observed between the resistance and ground. Taking readings at various points will allow identification of the resistance by narrowing down the section between normal and low readings. Care must be taken prior to testing to assure that all switches are in their normal operating condition and all connectors are intact. This is important since an open in the circuit between the test point and ground can allow the voltage in the circuit between the battery and the open to stabilize at battery voltage. The relatively small draw of a voltmeter will not result in a noticeable voltage drop, even through a significant resistance. The result will be a false indication that the circuit is good, with no abnormal resistance. Voltage readings taken after the circuit passes through the load should be zero, since this is the ground side of the circuit. If voltage is present, a significant resistance exists in the ground circuit back to the battery. If a voltmeter is not available, a test light can be used in the same way as a voltmeter, however with a lesser degree of accuracy. After testing and observing the brightness of the bulb when connecting directly across the battery, proceed with testing. A brilliant bulb is a good indication of a high voltage reading, and a dim glow from the bulb is an indicator of a low reading. Current flow, or amperage, is measured with an ammeter, and the value measured is read in amperes or just amps. Current flow measurement could be output from the charging system or current draw from electrical loads. While voltage is measured parallel to a circuit, the circuit must be opened and the meter installed in series into the circuit to measure amperage. This can be done by opening a connection or by placing the meter in series across an open switch. Care must be taken to assure the ammeter has sufficient capacity for the circuit being tested. Ohm meters are used to measure resistance in components or sections of a circuit. An ohm meter supplies its own power to the component or circuit being tested, so an ohm meter should never be used in an active, powered circuit. Like voltage, resistance is measured parallel to the component or circuit being tested. An ohm meter is connected to each end of a segment of the circuit that is suspected to have a circuit fault, and the resistance in that segment is read in ohms. If there are no working components or loads in the segment, resistance should be near zero. Higher resistance readings would indicate a continuity problem. If a component is being tested, you will need to know the resistance values for the component to make an accurate evaluation. Ohm meter readings of 0 ohms could indicate a short circuit, while very high readings could indicate an open circuit. Circuit diagrams and specifications are a key element for successful circuit testing. Using a diagram or schematic helps the technician identify all parts of a circuit and the location of logical test points. Specifications, especially for current draw and resistance, are necessary for complete analysis. Observing the basic theory which has been illustrated and following basic test procedures as demonstrated are necessary steps in the successful diagnosis of electrical problems. Applying these principles in advanced training programs will make analysis of more complex systems easy and accurate.